Adrian. And thanks, Anne, for the great talk that actually did a lot of the context work. So I'm going to be focusing, I don't know, on some permutation of these things. But yeah, so thanks everybody for coming. I'm Evan. This is some work that I've been doing with Adam, Daniel, and Ben over the past 2 years or so. It's been an effort to learn how to communicate across hydro and 1D boundaries, but I think we've finally started learning some cool things. And this movie is swirly, but we'll come back to it when we understand what's happening a bit better. So Anne talked about these convective boundaries. I'm going to have pictures like this a lot at the beginning of this talk so that we all kind of can like understand what processes are from simple pictures. We've got some sort of convection zone with turbulent overturning eddies. We've got a radiative zone with waves above that and a boundary between them that we don't understand. Let's call it the Schwarzschild boundary for now. And as we know, convective boundary mixing, as we are now calling it, perpetually makes us confused, like Doge. So if it helps, you can think of this as a small cutout on like the edge of a massive star. So like the blue fluid up here is some sort of stable fluid. The white stuff down here is the convective core. This is like a stellar context, but it's a box. Okay, so I'm gonna kind of talk from a fluid dynamical perspective about 3 specific processes that actually happen in like convection. They're all linked together to get to this convective penetration thing I want to talk about. And when I say convective overshoot, I'm not talking about like the class of convective boundary mixing things that we might call convective overshoot in 1D stellar models. I'm talking about a process which could also be referred to as mechanical overshoot. So let's say in our radiative zone, we have a characteristic buoyancy frequency N. We have a characteristic convective velocity down in the convection zone U. And as Anne was saying, the edge of the convection zone is where the convective velocity goes to 0. But that's not where the convective velocity goes to 0, right? That's where the acceleration changes sign. And so as convective motions go into the radiative zone, they get decelerated by the stable Brunt profile there. So motions don't stop there, they go above that line. If we think in terms of, say, physics 1, you can calculate a length scale using a velocity and a time scale. Well, the length scale we care about is the overshoot depth. We already have the velocity, it's the convective velocity. And the time scale is 1 over the Brunt frequency. This is kind of like a heuristic way of thinking about an overshoot depth. Works pretty well. And if you compare that overshoot length scale to, say, like the mixing length or like the average length scale of convective velocities, then you get something like the Mach number in stellar models, or 1 over the stiffness, or 1 over the square root of the stiffness if you're a fluids person. The point here is that low Mach number convection doesn't overshoot much. But this is like a persistent effect. So whether you're in a transitionary state or evolved state that's in full thermal equilibrium, you're going to have this motion because of the fact that like acceleration changes sign at that boundary. Okay, so that's overshoot. Let's talk briefly about entrainment. And when I say briefly, I mean like super briefly, because this is not my expertise. So this is a transient process. It happens in disequilibrium states, I mostly think. And lots of people have worked on it a lot over many years. So if we have this overshooting motion we just talked about, this overshooting motion can lead to entrainment, right? So these overshooting plumes mix some of this blue fluid down into the convection zone. That's entrainment. There's models of this going back 50 years to Turner. Is a thing that like starts off fast and gets slower like square root of time. It's a cool process. It makes our boundaries move. Okay, that's all I'm saying on entrainment. Okay, and now the rest of the talk is going to be focused on this third effect, convective penetration. And it's something that affects the structure of this boundary. So it affects the like thermal gradients, the entropy gradients, those sorts of things. Lots of people have done work that probably relates to penetration. There's a lot of simulations that either appear to have penetration in figures, but don't necessarily call it that, or maybe do call it that. It's confusing. There's some work that says maybe the extent of penetration regions depends on energy fluxes. I'm going to focus a bit on a couple of theoretical papers that we kind of combined in our recent work. So Ian Roxburgh did an integral constraint paper back in 1989, and Jean-Paul Zahn did a nice theory paper on convective penetration as well. So the way I like to think about this, we have this entrainment picture from the previous slide, and entrainment builds penetration zones. So we're overshooting, we're mixing, we're overshooting, we're mixing, and eventually we've pulled all the blue fluid out of this region, and now it's well mixed. This whole region is adiabatically stratified. The Schwarzschild boundary is somewhere within this adiabatically stratified convection zone, and the true dynamical boundary where the velocity goes to 0 is above that. So I'm going to call this a convective penetration region, a penetration zone, those sorts of things throughout the course of this talk. You could think of this as step overshoot in MESA models. It's a dynamical thing that happens, which is great. And so then the big question is, what's the size of that region? And hopefully by the end of this talk, you will understand that, at least as well as I do, which might not be perfectly. Okay, so let's kind of talk about a toy model of some energy fluxes in a star. So radiative flux, radiative conductivity, temperature gradient. We just have some sort of flux conducted along the temperature gradient. And let's say we have some sort of radiative conductivity, which increases linearly with height or radial coordinate, and there's a convective radiative boundary. So if we look at what the temperature gradient is, that's well mixed to some sort of adiabatic thing in the convection zone, falls off in the radiative zone, because thing that goes down times things that goes up equals constant equals total flux through the system. In pictures, looks like this. Radiative flux is increasing in the convection zone, and then becomes constant on the outside. There's some sort of total flux through the system. So the convective flux looks like that. And it's in thermal equilibrium, and everything is great, and we're happy, except for the fact that this can happen, and now we're not happy anymore. So what's going on here? So basically, convective motions have mixed the temperature gradient to the adiabatic beyond the Schwarzschild boundary. This means that this increasing conductivity causes the radiative flux to carry too much flux. And so convection has to make up for it and carry flux the wrong way. And we can see this visually. And we're going to spend a couple minutes here and walk through this. So these are 3D simulations in a box. These are like star in a box things, like Isabel was talking about yesterday. We have nominally a stable layer and an unstable layer, a convection zone and a radiative zone at the start of a simulation. We let it evolve, we let a penetration zone develop. This is the evolved state. On the left, we have the vertical velocity. Orange goes up, purple goes down. On the right, we have temperature perturbations compared to the background. So red is hot compared to its surroundings. Blue is cold compared to its surroundings. This is the buoyant variable. So red things want to accelerate up, blue things want to accelerate down. Okay, and what do we see? So there's 2 lines on each of these plots. There is a dashed line. That's the Schwarzschild boundary. In these simulations, we don't let that move over evolution. It would be good for us to do that in the future, like Anne was saying, because mixing changes that. But in these simulations, it doesn't move. And then there's the actual dynamical boundary. That is the edge of the adiabatically mixed region. That's where the gradient goes away from the adiabatic towards the radiative gradient. And it looks like a convection zone, right? Like if you look at the vertical velocity, you don't really see a difference across the Schwarzschild boundary. Upflows happen, downflows happen. But if you kind of correlate by eye, you can see that down here in the nominal convection zone, upflows are hot, downflows are cold. But if you get up in the penetration zone, upflows are cold. And downflows are confusing, but they're hot. So you have this anti-correlation between velocity and temperature perturbations. That's the opposite of what you would expect from a convective region. And we know this because, as we said on the previous slide, negative convective flux. And here's what the actual thermal profiles look like in the simulation. So I know this looks like a doodle because I've been putting a lot of doodles like on the slides, but this is actually the outputs of the simulation, time average, horizontally average. The purple line is the adiabatic gradient. The orange line is the radiative gradient. And the green line is the actual grad achieved in the simulations. So nominally, the Schwarzschild boundary is here, where the purple and orange lines cross each other. This is nominally a convective zone, nominally a radiative zone, but there is a large penetration zone where we mix to grad add past the Schwarzschild boundary. There's also like a weird little region here where we're falling off towards grad rad over a length scale. This length scale is proportional to that stiffness parameter I talked about earlier, or the Mach number. So in like a convective core boundary where the Mach number is 10 to the minus 4, this would almost look like a step function. Okay. So we looked at some simulations. We have some arguments about fluxes. Let's look just really quickly at an energy equation so that I can then wave my hands and not tell you the whole argument. So here's a kinetic energy equation. You have change in time of kinetic energy, divergence of fluxes. And the two terms I actually really want to focus on are these right-hand side terms, the sources and sinks. So you have a buoyant kinetic energy generation term and a viscous losses term. This looks like the viscous heating term in any code. So if you are conserving energy, this is going to be there. And this kind of argument I'm going through, I forgot to mention, Ian Roxburgh was the first to work through these sorts of arguments. So if you volume average or volume integrate this equation in time over the convection zone and penetration zone, the fluxes have no divergence at the boundaries. That goes to 0. If you assume your time stationary, so your kinetic energy is not changing, that term goes bye-bye, and you're left with this integral constraint. Buoyant work balances viscous losses. Now, nominal convection zones do positive buoyant work. This term is confusing. Ian Roxburgh said this is 0. You could say it's something greater than 0, but it's a number, let's say. And so the convection zone is going to do positive buoyant work and increase this number, because this is proportional to the convective flux. But then the penetration zone is going to do negative buoyant work and decrease that number. So you can only have so much penetration because this can't go below 0, and it's going to be fixed to whatever this value is over here, which is a number. So we take these equations and we make a parameterized theory and we do some stuff. And the punchline of it is that how negative this convective flux is here, the magnitude of that negative convective flux sets the size of the penetration region. And the negativeness of that flux is set by the conductivity profile in that layer, because it's set by how positive this radiative flux is here. So in pictures, let's say at the Schwarzschild boundary, you have a kink and your radiative conductivity gets really steep by having the adiabatic temperature gradient there. You're carrying way too much flux. So you have really strong negative convective flux, so it breaks itself really quickly and you have a short region. On the opposite side, you could have a kink going down. So this is really shallow. That's really shallow. That is also really shallow. And so the deceleration of these cold upflows is like a slow process in this case, and a fast process in this case. And that's what sets the extent of this region. This is basically the idea that Zahn had. He basically said, yeah, your radiative conductivity profile at the boundary sets grad rad, and this sets the depth of these zones. Daniel likes calling it grad grad rad, with like increasing, like subscripts, because he's a sadist. I mean, a very good person who I love working with. And yeah, so yeah, here's basically the proof of that concept. So each of these sets of 3 points is one simulation. And basically the thing we're changing in these simulations is that as we move to the right on each of these plots, we're having the conductivity profile get shallower in the radiation zone or penetration zone. And the y-axis is the size of that penetrative layer. And so indeed, shallower profile, less negative convective flux, larger penetration zone. And basically the difference between the two panels is that we did two different experiments to kind of try it out in two different models. This one, you have a constant conductivity in the convection zone, constant conductivity in the radiative zone. It's like a step function thing. So you get a slightly different scaling. And this one, it's what I showed on the previous slide. So you have like two lines that are connected. Works pretty well. There's some falling off of this like nice theoretical line because that dissipation term is hard. And here we assumed it was not hard when we made this orange line, because it's nice to make things not hard, but turbulence is hard. Okay, so the last thing I want to talk about is that we want to move this thing from 3D to MESA, right? This is kind of like the whole point of what we've been talking about. And so we derived a closed form from that integral constraint I talked about a couple slides ago, from those energy arguments, and it relates the radiative conductivity to the extent of the penetration zone. In MESA terms, it's in equation 44 in our paper. But Adam is great and implemented it in MESA for us. And then we threw it at a one solar mass model, specifically not a solar model. It has like a radius of like 1.04 solar radii and stuff, because it has like defaults in MESA. I learned that those are not the best. But anyways, so you can see that top panel is grads. There's a Schwarzschild boundary, grad rad crosses grad ad. And the actual gradient goes somewhat below that. And here is the differences in the sound speed with this penetration model compared to like a reference model that doesn't have penetration put into it. And you can see there's like a measurable acoustic glitch. This has the right sign to match acoustic glitches as are actually observed in the sun. It is too large because this is too deep. That's okay. So there's some obvious problems with the stuff we did here. We did this in the incompressible limit because we started based on the breathing pulses problem that Anne actually talked about. And we had like burning and composition and like opacity change with composition. And we were like pumped. And then we didn't understand anything. And so we stripped everything away and landed on, okay, now we think we understand penetration. And yeah, so now we want to expand it to stratified systems, like compressible equations. And the good thing is that the process of that integral constraint I talked about, stepping from there to a theory, should hold. So all we have to do is do it in the right equations and prove it. And there's also some kinks to work out in the MESA stuff. You can see this is not perfectly adiabatic. And my understanding is when Adam set grad to grad ad here, MESA was like, oh, this is all the convection zone. And then it did some weird things. So he tricked it and set it a little lower. So we got to fix that. And yeah, that's it. So we think we generally understand the process that makes these penetration zones work. We think we know how to get theory in all of the different contexts of how to explain it, but we need to expand it to all the fun contexts like magnetism and stratification and stuff, and nail down models and parameters. So thanks.
We've got 10 minutes. Who's got a question?
Okay, let's start with the question from the chat. Pascal Garot asks, is the initial radiative zone convection zone setup here entirely set by the assumed conductivity profile?
Yes. So there's a conductivity profile that varies in height that sets, and we set the grad ad to be a constant. And so the conductivity, which varies in height, makes it so that grad rad goes from being larger than grad ad to smaller than grad ad. Oh my God, grad rads and grad ads are hard. Yeah. So basically, there's a conductivity profile that makes these things vary in such a way that produces the Schwarzschild boundary.
Thanks.
Yeah, correct here. Thanks, Evan, for a great talk. Very interesting stuff. I've been puzzled by penetrative convection for a long time now, so it's good to see that somebody got it in 3D. My question is more clarifying question. What Rayleigh Prandtl numbers did you assume?
Yeah, so it's a bit confusing because we use internal heating, and so that let us decouple are convective motions from the radiative gradient. So Rayleigh number is a bit hard to define. The like measured Reynolds numbers in dataless with like explicit viscosity are something like a few thousand in the convection zone here. And we also went to smaller Reynolds numbers than that to do more parameter space coverage. I think in terms of like a classic Rayleigh number and Rayleigh-Bernard convection, I would call this probably like 10 to the 8 to 10 to the 9, probably 10 to the 9.
These are fully 3D though, right?
Yeah.
Yeah.
So we only did a couple at this level of turbulence, and then mostly did less turbulent ones to expand the parameter space.
And did you get any scaling laws based on the Reynolds numbers or other input parameters?
Yeah, so I don't have it in here, but so we found strong scaling of the penetration zone with basically this conductivity profile. We found strong scaling of the width of this region with the stiffness, so basically the Brunt frequency up here. And we found a slight logarithmic scaling of the dissipation with the Reynolds number. It's hard to disentangle what's happening there from boundary effects. We think it's mostly boundary effects, but yeah. As far as what this zone is doing, there's a slight, the dissipation causes this to change a little bit, but it's mostly the profiles.
Other questions?
Radek Smoles here. I'm a bit confused with this definition of convective boundary in evolutionary code in 1D and in 3D. So in Antox, the convective boundary was defined as a place where velocity vanished. And it resulted from the application of Schwarzschild criterion on the convective side. And here, this Schwarzschild condition, can you go back to this slide with simulation?
Yeah.
So the dashed line here is a Schwarzschild boundary at which acceleration vanishes, right?
Yeah, it's where acceleration vanishes and changes sign.
And the true boundary is where the velocity vanishes.
Yep. Yeah, that's up here.
So this convective penetration region in the framework of 1D codes is actually below the convective boundary, right?
It's beyond.
I'm just confused with this acceleration vanishes versus velocity vanishes.
Right. So yeah, acceleration changes sign here, velocity vanishes up here. I think from what Anne was saying, the convective boundary in MESA would be found to be the dashed line. No? It would go above it.
It would be where the velocity vanishes. That's the 1D mixing length theory conundrum.
Right, okay, but MESA doesn't have the 3D dynamics, and so it doesn't know where the velocities vanish, so I think it would assume velocities vanish at like the...
It assumes, so within the mixing length theory, the velocity vanishes where the two grads are equal.
Okay, so yeah, then they would vanish here in the MESA model, I believe. And so this is a simulation where we've cranked up that, or I guess cranked down the steepness of that conductivity profile so that we have like a bonkers large penetration zone so we can show it in a movie. We expect the ones that actually show up in stars to be smaller than this, but this is like a proof of concept movie.
Pascal Garot wants to add that MLT is usually used in a local framework, whereas the DNS show that the flows are not local. And I think that might explain some of these differences.
And in fact, that integral constraint we were talking about is a global integral over this whole region. So,
Other questions?
I thought that your explanations were really illuminating and very, sorry, Paul Kerwig. very illuminating and very clear. So that's really great. My question is this, and you mentioned that one of the things missing is the concentration gradient. And so my question is, do you have a feeling for what happens when you do add that? Because what N is talking about is that when you are starting to mix into that penetration zone, then somewhere FRAD will encounter this decrease of thermal diffusivity, and so it will go down, right? So it goes up as you go across your Schwarzschild boundary, but then can go down again as you are encountering the hydrogen gradient. And so there is, a very interesting dynamic interaction that I think will have to play out. What is your feeling how that will ultimately settle where this penetration zone ends up?
Yeah, so you're referring to like the fact that entraining fluid of a different composition changes the conductivity profile, or that's like the important question you want me to get at, right? Yeah. So as you entrain, like let's say you started your convective zone here and it worked its way up and it entrained fluid up here of a different composition, that would change the conductivity profile, and so that would make the Schwarzschild boundary move. My impression is that if the Schwarzschild boundary moved up to here, this whole zone would still be doing positive buoyancy work, and so you'd still have a penetration zone past that. There would eventually be an equilibrium state where, because I'm assuming that, like, if you mix this much fluid, it doesn't change the Schwarzschild boundary by an equal amount. So it would change where the equilibrium is, but I think this process would still hold.
Hi, Evan. Oh, well, it's loud, sorry. Tim Cunningham here from the University of Warwick. Thanks for the talk. Yeah, I had a couple of questions. One is, how does your velocity profile through the penetration zone actually look? Like, we've seen the video, but how does it look as a horizontally average profile and time average profile? How does that compare to the F overshoot parameter that's often employed in 1D models? And what value of F overshoot would you need to fit that velocity profile?
Yeah, so I think the F overshoot stuff would be in this region here, and Lydia did some great work on that a couple years ago. I haven't fit an F overshoot to this, so I don't know offhand. As far as what's happening in this region with the velocity, you basically have like a kind of constant-ish velocity profile in the convection zone, and then it sort of falls off a bit, and then it falls off steeply near the boundary. I have movies of that I can show you if you're interested. I don't have them in the talk, but it's lower velocity than the convection zone, but it doesn't like linearly fall off or anything like that. It kind of comes down a bit and then hits this boundary layer where the F overshooting happens. Does that answer this question?
Yeah, it does. I don't know enough about the F overshoot implementation in MESA, but I thought that would happen at the Schwarzschild boundary.
Yeah.
Not at your penetration zone boundary.
That is exactly also what we thought when we started this project. So
Okay.
we were very confused. I think Jamie has a question, and
Sure. So I thought your glitch signature, Jamie Tyre, I thought your glitch signature was really interesting. Have you thought about other places you can test to see if this is the right size and the right sign and the right scaling?
Yeah, so Adam started kind of throwing these at massive star exams, or main sequence, not just SAMs, models. I think it is still a bit too large. So we think that this is partially probably from the geometry. Falk's been showing great movies of like the fact that we have dipole flows instead of, rolls like we have in these local box models. So that probably changes the dissipation and thus the depth of this. That's one of our parameters. And the stratification is like the big thing that I think we really need to just sit down and make sure we get that figured out and get it into models. But yes, we are trying to actually apply this and see if it does any help with observations.
All right, with that, let's thank Evan again.